In this section, 8.2, we get into a lot more of the meat of hypothesis testing, how to do it rather than just kind of what it is. So we're going to look, and again, we're going to go through 8.2, z-test for a mean. It's the objectives we're going farther in. And we're going to go through 5 steps of hypothesis testing, test mean when sigma is known using the z-test. And that's as far as we're going on the objectives for 8.2. So, the z-test for a mean. The z-test is a statistical test for the mean of the population. It can be used when n is greater than or equal to 30. So you can use it with a sample size of a sample standard deviation if your sample size is large enough. And that's key piece of information. So if n is greater than or equal to 30, then you can use the z-test rather than the t-test. When your sample size is small, you're going to have to use the t-test. You know, just like we learned the t-test last unit. When the population is normally distributed, which that should be said, and sigma is known, you know the population standard deviation. So the formula for the z-test is right here. Z equals x bar minus mu over sigma divided by the square root of n. You've seen this before. This is not a new formula for you. You've seen this z formula before. And so you can see here they've listed everything that's given in the problem, or you should list what's given in the problem. So let's go on and look at an example. This is example 8.3 on page 414. There's a researcher wants to see if the mean or the average number of days that a basic low price small automobile sits on a dealer's lot is 29. You have a sample of 30 automobile dealers and a mean of 30.1 days for basic low price small automobiles. At alpha 0.05, test the claim that the mean time is greater than 29 days. The standard deviation of the population is 3.8 days. All right, now on the next slide, there's going to be some of this stuff typed out, but let's just look at this. We've got, first, we can list our we have our X bar. And that's at 30.1 days. And the mu is 29 days. Alpha is 0.05. And we have the standard deviation of the population is 3.8 days. Okay. So we know all those things. Oh, and our sample size is 30. So n, oops, dropped my pen, excuse me. N equals 30. Okay. So we've got all that information. Now we need our hypotheses. Okay, our null hypothesis is that mu is equal to 29. Okay. And our claim, our alternate hypothesis, is going to be, let's see, let's look for the words. A researcher wishes to see if the mean number of days sits on a dealer's lot is 29. You have a sample of 30 automobile dealers has a mean of 30.1 days. Just checking to make sure I did that right. I sometimes get them backwards. Okay, a researcher wishes to see if okay, so H bar mu is equal to 29. H1, I shouldn't have put an equal sign there. I'm going to have to clear that off. Let's see if it'll clear. Yeah. All right, we want to see that the mean time is greater than 21 days. There it is. I was looking for words and didn't see them in the first part. Greater than 29 days. So the null hypothesis is that it is 29 days. Our alternate hypothesis will be that it is greater than 29 days. So then we've got our next slide, which shows all that. State the hypotheses, which we just did. Identify the claim. Find the critical value. We haven't done that yet. We listed all our variables. So we know X bar is 30.1, mu is 29, sigma was 3.8, and the sample size was 30. So we plug those in right there and find the z-score of the test value. That's our test is 1.59. But alpha, the alpha z-score is up here in step 2, our critical value. Alpha is 0.05. The test is right-tailed because it's greater than. So if you remember, you're going to draw your curve, okay? And you're going to locate, here's your mean, here's your value at alpha 0.05, right? And remember that means that we have the right-tailed test here is what we're looking for. That's our critical region, if you want to label that. Okay, so we could write here, critical region. Remember that from section 1. And then our non-critical region is all this in here. Non-critical region, and our critical value is that border, that cutoff score, or whatever you want to call it, between the two regions. And so we look up our alpha at 0.05, right-tailed test, and some of these you'll start to memorize. If it's right or left-tailed, 0.05, that's 1.65. And you might start even making yourself a note, and so you don't have to look them up every time. So this is 1.65, that's our z-score. Well, we've got a calculated value of 1.59. Well, that's going to be over here. Okay, our test value is 1.59. It's less. So where does that fall? Well, we can see it falls in the non-critical region. And so this is a better scale drawing, obviously typed up and looking nice. So we have to make the decision. The test value is less than the critical value, so it's not in the critical region. We decided that. So the decision is to not reject the null hypothesis, because our claim was the alternative hypothesis. And so we make our summary statement. There is not enough evidence to support the claim that the mean time is greater than 29 days. Okay? And so you do need to make this summary statement, when you do your work, when you finish your work. Because if you don't, if you just show me a critical value z-score and a test z-score, I don't know what conclusion you've drawn. And the hypothesis, the whole point of this hypothesis testing, is that you're going to draw a conclusion at the end of the day, at the end of running your data, if you're a real researcher, running your data and analyzing it, and then you're going to draw a conclusion. And that's really what statistics is all about, is analyzing data and figuring out, what it's telling you. So, one thing to note here, the sample mean, 30.1, is higher than the hypothesized population mean, but it's not significantly higher. It's not enough higher that it was due to the test. It could have been, remember in Unit 7 we came up with this range, and it could have fallen into that normal range of population, the spread of your population distribution if you pull out a sample. And so what that tells you, though, is that you may have made a mistake. I mean, it's the closer they are together, the more likely that you might make one of those errors where you reject the null when you should have kept it, or kept the null when you should have rejected it, the type 1 or type 2 error. So the difference probably it probably isn't significant, but there is a difference in statistical significance because we set that alpha or significance that really might make that really is there. And so there's always that chance for error. And when they're close together like this, that chance is greater. So we did not reject the null, but there's a probability of type 2 error here that we should have rejected it. That it was so close that perhaps, we made a mistake. But you have to have a standard. You have to have some cutoff score and make that decision. And you need to set that standard, that alpha, when you're running data analysis. You need to set the standard you're going to call statistically significant before you run your test, not after. So here's another example on page 415. Here we've got a lot of data, so you're going to have to run your stats. A researcher claims that the average cost of men's athletic shoes is less than $80. He has a random sample of 36, so there's my N, and finds the following cost in dollars. The costs have been rounded to the nearest dollar. Is there enough evidence to support the researcher's claim at alpha 0.1? Assume that sigma is 19.2. So you're going to run your data and get your mean from your 1var stats. We know that there's 36 pairs of shoes. We know that's your N. And so here's our step 1, right? Our hypothesis and our claim. That's important because you have to say something about that at the end of the day when you're done with your problem. So our hypothesis is that mu equals $80, and our claim is that mu is less than $80. Step 2 here, find the critical value. So we're looking at an alpha of 0.1. It's a left tail test because we're wanting less than. So, if you're drawing your quick curve here, we're right here, and alpha is 0.1. So we have 0.1 here, and that means we've got 0.9 out here, right? But the thing is, we're looking in this area, and when we look at our z-score, it tells us to the left. So it's not quite as critical on these that we know what that other area is, because the z-table tells us the area to the left of the z-score. All right, so when we look that up, we look up alpha 0.1. This is what we're going to go inside the table and find, and then read left and up what our z-score is, and it's negative 1.28. So it's negative 1.28, and that's our critical value. That's our borderline. That's our score that we're going to compare our test z-score to. So we're going to go on. This time we're doing step 3, computing the test value. So we've got our x bar is 75. That was what we calculated from our 1var stats. Sigma was given in the problem, 19.2. We know our sample size is 36. And we know our average, our mu, is 80. So we plug all those in right here to our formula for calculating z, and we find a negative 1.56. So we put that on our chart, and here's a prettier chart than the one I drew, but we see that 1.56 right here falls in the critical region. So there is enough evidence to support the claim that the average cost of men's athletic shoes is less than $80. Okay, so it fell in the critical region, so the claim was supported. All right, this is 8.5, page 416. Medical Rehabilitation Education Foundation, that the average cost of rehabilitation for stroke victims is $24,672. To see if the average cost of rehabilitation is different at a particular hospital, a researcher selects a random sample of 35 stroke victims at the hospital and finds the average cost of their rehabilitation is $26,343. So here, if we're going to go in here, this is our mu, this is our x bar, and this is our n right here. And here's your alpha. I like to list them rather than go in and label them, but you can do that if you want to. And so we want, at alpha 0.01, can it be concluded that the average cost of stroke rehabilitation at a particular hospital is different, not greater than or less than, just different. And so that makes our symbol that we're looking for not equal to. It can be, this is going to be a two-tailed test. It can be less than, and it can also be greater than, and it still be different. So we have our hypothesis and the claim right here. Whoops. Right here. The null hypothesis is that the mu is $24,672, and the claim is that mu is not equal to $24,672. It would fall outside the non-critical region. It'll fall in the critical region, but that critical region is on either side of, in either tail. So we have a cost, again, this is step 2, finding the critical value. We have alpha 0.01, a two-tailed test, so that means there's 0.005 in each tail, and we found on those that our z is plus or minus 2.58. So we put that on a nice bell curve that we've drawn. Oh, well, we calculate it first, find the test value, sorry. So we put our values in here, our x bar, our mu, our sigma, and our population size. And we looked at, sigma I think we might have had to get from 1-bar stats too. I don't remember now if that problem said the sigma, but if it didn't, then you had to get that when you'd ran your stats. So we have 3.04 as our test value. So we're going to look here. We have to make our decision. So we're going to go. We have 2.58. We have 1.01. Not sure what that is. And we have 3.04, which our value was up here somewhere. Whoops. I think that's maybe a wrong chart that's in here. So our 3.04 is really significant. It's up there in that upper critical region. So there is enough evidence to support the claim that the average cost of rehabilitation at the particular hospital is different from $24,672. So we had when we did our calculation, we find that it does fall in that upper critical region. Okay. Now there's a p-value, or probability. I'm not going to put these on your test. I'm just going to tell you right now. This is not going to be on the test. The z-score will be. But there's probably some of these in your homework. P-value or probability value is the probability of getting a sample statistic such as the mean or more extreme sample statistic in the direction of the alternative hypothesis when the null hypothesis is true. So and it's really a very similar test. You're just going through and finding probabilities. So the traditional method for solving hypothesis testing problems compares z-values, that's what we just did, a critical value and a test value. The p-value method compares areas, the alpha and that we know in the p-value. And actually I may put one of these on the test, but there is a later piece that I won't. So we have steps: state the hypothesis, identify the claim, compute the test value, find the p-value, make the decision, summarize the results. The steps are really the same, it's just we're doing a p instead of a z. So this is example 8.6 on page 419. It has to do with the cost of college tuition. A researcher wishes to test the claim that the average cost of tuition and fees at a four-year public college is greater than $5,700. This problem was written some time ago. She selects a random sample of 36 four-year public colleges and finds the mean to be 5,950. The population standard deviation, or sigma, is 659. Is there evidence to support the claim at alpha 0.05? Use the p-value method. So our hypothesis, we're looking at greater than, so that's our H1 right there. And our null hypothesis is that mu is equal to the 5,700. So look for the words in there to find your claim. So that's step one. Step two, compute the test value. So we've got 5950 minus 5700 divided by 659 divided by the square root of 36, and we get 2.28 for our test value. And our p-value, we go to the table and find the area for z 2.28. So remember, you go read 2.28 and then go down into the table and find the area, and the area is 0.9887. Well, okay, we're going to draw our little quickie curve here. There's our zero mean. Here's 2.28. Well, then when we read from our table that our area is 0.9887, remember that's in here. That's to the left of that value. And we need to know our tail. We need to know how much area is, this is the area we're looking at, not the larger area. So we have to go in, excuse me, and find the p-value in just the tail. So we subtract it from 1, and we find that the p-value here is 0.0113. So this value here in our tail is 0.0113. Okay. So here we are making our decision. The p-value is less than 0.05. Okay, so we found this score that corresponded to our area. We just calculated all this and looked it up in the table. Our area that was given in the problem right here, this was our alpha, and that was given in our problem, the 0.05. And so we marked that. So really, what I should have done on that previous slide, I was treating that like a critical value. We are looking for the tail. Let me go back to that slide. See, we are looking for this in the tail, but 2.28 was not our critical value. This was our test value. Okay, and so we don't really know. This is what I should take off, is this coloration. We don't really know whether it's going to fall in the critical region or not. Okay, we do know these numbers. That's not wrong, but we don't know where it falls. we have an alpha of 0.05 that we've got to put on here somewhere. Okay, so our 0.05 is over here, again, like we just showed on the, okay, so all of this is the alpha. And we just showed that on the better slide, but I wanted to go back and fix this slide. So, here we go with our better slide. The alpha was given. We do fall in that critical region. So there is enough evidence to support the claim that tuition and fees at a four-year public college are greater than $5,700 at an alpha of 0.05. Now this is in a little note. This is where your statistical, how you set up your test makes a difference. Here, if we had set our alpha at 0.01, then we would have retained the null. We would have said it's not rejected. And so setting that, and you can't finagle that after you start, after you get your results, because then it's interpreted that you're making your results do what you want it to do. So we set our alpha beforehand at 0.05, and we said we're going to be satisfied with however this comes out with this level of significance. And it said in this case that we reject the claim, or support the claim, excuse me, reject the null. Now, if you wanted to do another test later and set up your different alpha, that's perfectly fine. But for the test that you're running, you always do the alpha before you start. And in your case, it's given in the problem. All right, here is another hypothesis testing 8.7, example 8.7. Researcher claims that the average wind speed in a certain city is 8 miles an hour. You have a sample of 32 days. Notice these sample sizes are always bigger than 30. Standard deviation of the population is 0.6. And you have your average wind speed of 8.2 miles an hour. Okay, so our mu is equal to 8. Now notice, the standard, is there enough average wind speed? So his claim is the average wind speed is 8 miles an hour. And our sample, is there enough evidence to reject the claim? So his claim is that it is 8 miles per hour. Well, this experimenter set that up as the null instead of saying the average wind speed. So our claim is our null hypothesis, and that's a little different. I personally don't like to do it that way because I think it makes it more confusing. But the hypothesis, you set the claim, was that mu is equal to 8, and mu is not equal to 8 is your alternative hypothesis. We get our test value as 1.89. The p-value for 1.89 is 0.9706. Now this is a two-tailed test. So we find our area is 0.0294 here. And so in this case, we double that area instead of halving it like we did. It's not really, it's a difference. This time it's area. So they're going to double it. Now let's look at a picture because that will help. So we have our decision is to not reject the null. P-value is greater than 0.05. So our alpha that we're looking for is 0.025, and let's get goes back here. Here we go, alpha of 0.05. So that means there's 0.025 in each of the tails, and you can see that that's drawn on your curve here and here. So our alpha we did divide by 2, and we put it on our chart, and we colored in where the claim region, where the critical region is. So those alphas were set and divided by 2, just like we did. That part's not different. Then our p-value was 0.0294. I'm going to go back and see. That was right here, and that's what we calculated. So we've got our probability, our area. You're going to put that 0.0294 in each tail. Okay, so here's an area of 0.0294 here, and here's an area of 0.0294 here. Now, our null was 8. Our claim was 8.2. I mean, our null was our claim. So in this case, and this is, sometimes I have to, this is our claim. Our null is our claim, which is very different than what we're used to looking at. So our null is our claim, and 8.2. So there's not enough evidence to reject the claim that the average wind speed is 8 miles per hour because we didn't fall in the critical region. 8.2 can be simply a result of normal the variation. The range you'd find as you pull out different samples and calculate their means, again, falls within a range, a low to high range, somewhere around the population mean. Okay, now this is the slide where I'm going to say, just, this is guidelines for P with no alpha. I am not going to give you any kind of problem where there's no alpha. So you can just forget this slide in terms of learning and needing to know this for your test. So it's just not something I'm going to worry about on the test. I'm going to give you an alpha. And I won't give you too many of the probability ones. I'm going to do more of the z-score ones on the test. But anyway, just so you know, this is something, how to do, but it is good information, how to know whether to reject the null or keep it, and the results that might give you a type 1 or type 2 error. But it is difficult. In any problem I give you, there will be an alpha.